Hello there, I'm Harold Schuch. I'm a lecturer at the Department of Civil Engineering at the University of Colorado, Denver. This module deals with automatic levels. These are devices that are used for the purposes of surveying in the engineering world. Let's say there is a job requirement. A building must be built that is level and it's located at the right elevation. Those are normally requirements that are frequently found in most construction projects. The tools that are used to achieve that are an automatic level, which is an instrument that is used to establish a horizontal plane throughout the construction site. So here we can see, for instance, that the reading here is the same as the reading here on these leveling rods or level rods. These are like rulers that have 0 at the bottom where they touch the ground, actually stand on the ground. And with this, we can get the distance between the ground and the instrument. Now, to use the instrument, we need 3 important parts. The instrument itself, the automatic level, a tripod on which this instrument is standing, and a leveling rod. There may be more than one rod. Now, looking at the instrument in more detail, the parts of the automatic level consists of a telescope at the top, where this is the front and this is the back. This is the eyepiece through which the operator looks, and this is a focusing ring for the eyepiece. This is to focus the crosshairs. And then there is a telescope focusing knob. This is used to focus the image that comes in from the telescope. If we want to do some fine aiming horizontally, left and right, we can use this fine aiming knob. Then the instrument has a bottom part that is called a tribrach. The tribrach has 2 important things. First, it has 3 leveling screws that are used to level the instrument. And in addition to that, it has a threaded hole in the middle that allows a screw to be screwed into the base of the tribrach to secure the instrument against the tripod. Now, somewhere on this flat surface on the other side of the instrument, there is a leveling bubble. Note that this leveling bubble has above the bubble itself a ring etched into its glass surface. Now, as we look through the telescope, we would see whatever scenery is in the field of view, and in front of it, we would see a leveling rod, normally held by somebody for the purpose of holding it vertically above a certain point. Then we will see 4 crosshairs. 1 vertical crosshair and 3 horizontal crosshairs. The vertical crosshair is not very relevant, but the 3 horizontal ones are. The center crosshair is used for leveling. This is used to read the rod in most cases. However, for some purposes, the center crosshair reading is accompanied by an upper crosshair reading and a lower crosshair reading. If we take this reading and subtract this reading, and we multiply this distance that we read times 100, then we have the distance between the telescope, between the instrument, and the leveling rod. If we are in a situation where we cannot easily repeat a reading or a project, if it's very delicate for us to be certain that we read things correctly, one way to avoid errors before one moves the instrument is to take the upper reading plus the lower reading and dividing that by 2. And that should be equal to my center reading. In other words, I have a way of detecting errors quickly before I move the instrument. Those 2 purposes are listed here and here with the corresponding equations. Now, when it comes to reading the leveling rod, most people have some difficulties in doing that, at least initially. So here we're going to do a little exercise. Here we have an arrow that would indicate where a certain center crosshair would come across the leveling rod. So this value here equals 3 feet, 0.89. And that was what I've listed here. In this case, if the crosshair goes across here, this reading would be 3 feet, 0.52. That's what we have here. Now, these leveling rods are telescopic rods. That means that they come collapsed, they push together, and to use them properly, they have to be extended, because if they're not extended, then reading errors will occur. So therefore, make sure that every time you use one of these leveling rods, you make sure to fully extend this telescopic rod. To do the surveying with the instrument, there are certain parts that are important in the setup. For instance, if we look at the tripod has clamps and is built in segments. If one loses one clamp, then this segment will slide up for easy transportation. However, this is also used for rough leveling, as we will see. Then the feet of the tripod are sharp, so they will easily find a spot on the ground where they don't slide around. That is very important. If one is on soft ground, then some surveyors will step on this ledge and push the tip into the soft ground to firm up the position of the tripod. Then, of course, there is the bubble on top of the instrument, and one can use these leveling screws and the lengths of these legs to bring this bubble to the center or close to the center. Why am I saying close to the center and not to the center? If the bubble is at least is split by this ring, then the instrument will take over and finish the leveling for you. That's why it's called an automatic level. This instrument has a pendulum inside, an optical pendulum that allows the last bit of leveling to be done automatically. So the instrument is a delicate instrument. You can shake it and you can hear the pendulum rattling inside. You may not want to shake it too hard or bang it because you may damage that pendulum, which is made up of optical glass parts. However, there is some protection inside. There is a clear liquid that damps the movement of this pendulum. Some instruments allow you to turn a knob and to clamp down this pendulum for transport. In this case, this instrument itself does not have that kind of feature. And then there is the focusing of the level. As I mentioned, there are two focusing knobs, one for the crosshairs and one for the telescope. It is very important to first focus the crosshairs and adjust the crosshairs to your vision, and only then adjust the field of view of the telescope. This assures that both images, the image of the telescope and the image of the crosshair, end up in the same focal plane. That means that those images will not move with respect to each other. Therefore, it's important to first do the focusing of the crosshairs and only then do the focusing of the telescope. Then one guarantees that the two focal planes will coincide and there will be no movement that could falsify readings. Now let's see how these instruments are used. There is a very basic leveling geometry that is as follows. You'd be surprised how simple this is. Let's say we have a point A, and we have the elevation of point A. We know this elevation, and we want to establish the elevation of point B. Then we put a leveling rod on point A and set up the instrument anywhere convenient from where we can see both points. We level the instrument and we take a reading back towards point A. This is called the backside. Then we turn the instrument around to point B. We take this leveling rod over to point B, and then we take a foreside reading. So the elevation of point B will that then be the elevation of point A plus the backside reading minus the foresight reading. And that's the whole secret about leveling. Now, in this process that I just described, we gain something that is called the height of instrument, which is really an elevation. The height of instrument in this moment is the elevation of point A plus the backside reading. That gives me the height of instrument. And you may want to study this text and these equations because they repeat what I just said. Of course, this is only between 2 points. What if we have more points involved? Then one just hopscotch along from point to point. First between point A and point B, then repeat the same process between point B and point C, as shown on this slide. Now this here is called a traverse. We're starting from one point, set up the instrument between this point with a known elevation and this point for which we want to know the elevation. We take a backside and a foresight reading. That gives us this elevation. Then we move the instrument from here to here, take a backside reading and a foresight reading, then move the instrument to here, backside reading, foresight reading, and finally set up here, backside and foresight. Now, obviously, with these two readings, we can calculate the elevation of this point because we know, for starters, the elevation of this point. Then once we have this elevation, we can calculate the elevation of this point, and so on, and so on. That means we come back to our starting point, we can recalculate the elevation of the starting point. Obviously, we should come back to the same elevation. However, we will have reading errors and other things coming along the path, along the traverse, so that the elevation we calculate for this point coming back will be different than the elevation that is given for that point. The difference is called a misclosure. If this misclosure is large enough that it needs to be dealt with, if it's too large, then we have to repeat these measurements. If it's acceptable, then we can find a way of adjusting these readings for the purpose of coming up with a zero difference here. Now, you will notice that these points are called TP, TP, TP. That is because if you have the instrument here and you look at the rod from this side, then you have a foresight taken here. Then as you move the instrument over here and you look at the rod from this end, you have to turn this rod around so that the numbers can be seen from this point. That is why these points are called turning points. It's where the rod is turned. Well, thank you very much. This is the first module in relation to the automatic level. And there is another module that follows this that has to do with the adjustment of a level traverse. And that module is called vertical traversing. I hope to see you then. Thank you. Bye-bye.